Hi everybody, I hope you've enjoyed the showcase so far. My name is Kyle Fortenberry. I'm the Senior Optical Thin Film Coating Engineer at PFG Precision Optics. We're an optical fabrication and coating house located in Ocean Springs, right on the Gulf Coast of Mississippi. Thanks for taking the time to listen today. I'm going to talk about some stress control strategies that we use at PFG when coating high aspect ratio substrates and how to maintain their flatness during the coating process. So let's start by talking about the problem. Well, I think oftentimes fabrication and coating are viewed as two independent, unrelated processes. But I think as any good optical manufacturer will tell you, those two really interplay with each other to produce a high quality optic. One place that's true is in surface flatness. The reason for this is because coatings contain stress. And as the parts are coated, the coating stress bends the optic and makes a change in their surface flatness. We'll talk in a minute about where the stress comes from and what we can do about it. But this problem is exacerbated on high aspect ratio parts where the OD to CT ratio approaches a value of roughly 10:1 or greater. Now this is not a hard spec. It depends on the flatness trying to be achieved and the coating that's going to be applied to the optic. But for sort of industry standard tolerances, this can be a good rule of thumb to follow. So who should care about this? Well, it's really a design for manufacturability problem. As optical designers and engineers try to design and tolerance optical systems that might contain high aspect ratio parts, they should have a good understanding of the difficulties in manufacturing the parts that they're trying to design and understand the processes necessary to achieve these specs. Optical buyers might also be interested in why this high quality part might command a certain price or delivery. So as I mentioned, coating stress is the root cause for this flatness change and is the crux of the problem. Coating stress is classified as either tensile or compressive. In tensile stress, the coatings tend to want to contract, and as they do, they pull in on the coated surface and induce a concave change in flatness. In the diagram on the left, the top surface of this optic is coated, and as that coating contracts, it pulls inward to change in the concave direction. The inverse of this is compressive stress. Again, in this diagram on the right, the top surface is coated. In compressive stress, the coating tries to expand and it pushes outward on this coated surface to create a convex change in flatness. So where does the stress come from? One place is due to thermal effects, namely the mismatch in thermal expansion between the coatings and the substrate. One reason for this is the differing CTEs between the coating materials and the substrate. But also, for example, in typical evaporative depositions, the coating material must be heated to its evaporation temperature. Usually this is at least 3 to 4 times that of the substrate. So this means that as the coating is deposited, it's put down in a much greater state of expansion, such that as the coating is cooled down after it's complete and everything returns to atmospheric conditions, the coating film contracts more than the substrate, and this induces a tensile stress. Almost always thermal effects will induce a tensile stress. Another reason for coating stress is the atomic and molecular structure of the coating itself. So there are some coating materials and some coating processes which generate a very porous film. And this means that the atoms are put down at an atomic separation that's too large. And as a result, the atoms want to pull together and the coating tends to try to contract. This induces a tensile stress and a concave change in flatness. Alternatively, there are other coating materials and coating processes, namely highly energetic processes, that really create a high packing density. And in these films, the atoms are packed in too close together, and so they try to push each other apart, and the coating tends to expand, creating a compressive stress and a convex change in flatness. So in general, Low energy processes produce tensile stress, whereas high energy processes produce compressive stress. Now we characterize flatness change due to coating stress with Stoney's equation. You can find this equation in the upper left-hand corner. It gives you the change in flatness in fringes due to the coating stress. And it contains many variables. For example, there's Poisson's ratio and the Young's modulus of the substrate, which characterize the mechanical properties of your substrate. What you'll also find is the aspect ratio, D over TS, where D is the diameter and TS is the thickness of the substrate. Notice that this is found as D over TS squared, whereas all other variables in this equation are linear. This would imply that the aspect ratio is the most important and most sensitive factor in determining the flatness change due to coating stress. So for example, here are two identical substrates. They differ only in their aspect ratio, and they're coated with identical coatings. The optic on the left has an aspect ratio of 4:1, and Stoney's equation gives us a flatness change due to the coating stress of about 1/3 of a fringe. The optic on the right has an aspect ratio of 8:1, and we calculate a flatness change of 1.32 fringes. So we see that since the aspect ratio is twice as large on the optic on the right, the flatness change is 4 times as large. This is due to the fact that it's aspect ratio squared in Stoney's equation. So what we take from this is that the aspect ratio is the easiest and most sensitive thing to control in trying to maintain flatness during the coating processes. So returning to the previous slide for Stoney's equation, we notice the only two variables present relative to the coating is TF, the thickness of the film, and sigma, the stress coefficient of the film. However, typically, the thickness of the coating is pretty well fixed by the optical characteristics. For example, the reflectivity and or the bandwidth trying to be achieved pretty well fixes the thickness of the coating into a pretty narrow window. So as a result, the stress coefficient is really the only variable we have to play with here to try to minimize the flatness change. So with that in mind, let's take a look at a few different strategies we can use that we employ all the time at PFG to maintain the flatness and minimize the effects of coating stress. The first thing we can do is take a very close look at our choice of coating materials. This is because some coating materials in any given process produce tensile stress, whereas others can produce a compressive stress. So if you combine them in the proper combinations and with the proper relative thicknesses, you can counteract the stress of the individual layers such that the overall stress of the coating is as close to zero as possible. You're of course, limited by your ability to meet the optical requirements of the coating. Also, any environmental durability testing you have to survive, or perhaps even laser damage threshold. But generally, it's possible to find the right combination of materials that, when put in the proper relative thicknesses, will produce a stress-free coating. What's required to do this is extensive characterization of your coating materials and a good understanding of their individual stresses so that you can calculate the relative thicknesses necessary. The second thing we can do at PFG is use ion-assisted deposition. Typical E-beam or resistive evaporation produces tensile stress in the coatings. That's because these are low energy processes. In ion-assisted deposition, an ion source is added to the process to provide some energy and increase the packing density of the coating. This drives the stress in the more compressive direction with the goal of trying to achieve a stress-free coating. Now, there are other coating processes, for example, sputtering, that produce even more energy than IAD does. However, they're often too compressive, and there's not a lot that can be done about it. IAD has the advantage of being flexible in that you can adjust the parameters to control the amount of packing density you get and control the stress. You can even turn the ion source off if you're trying to get tensile stress or use it when you want compressive stress. Furthermore, ion-assisted deposition doesn't limit your coating material choices, whereas sputtering has a very limited database of coating materials available. Ion-assisted deposition still allows you to use almost any coating material you like because it's simply an enhancement. And so option 1 of coating material choice is still in play with ion-assisted deposition. Option number 3 is to do a post-coat anneal. As I mentioned before, thermal stresses almost always induce a tensile stress. So if you're using a high energy process such as IAD or sputtering that produce stress that's too compressive, you can do a post-coat anneal to drive that stress in the tensile direction, again with the goal of getting that as close to 0 as you can. You are limited, however, by the transformation temperature of your glass that you cannot exceed. Also, there are some studies that show that the wrong anneal temperature can be detrimental to your laser damage threshold. So you have to be careful when employing this method, but oftentimes it's possible to find the proper anneal temperature and time that will reduce the stress of a compressive coating and get it very near neutral. Another option is to employ a back surface coating, that is to coat both sides of the optic so that the stresses counterbalance and maintain flatness. This is oftentimes done for anti-reflective coatings. Both sides of the optic are coated with the same coating. However, you can also do this with high reflective and filter coatings. For example, you can take part of a filter and put it on one side and take another part of a filter and put it on the other side such that their stresses counterbalance. You have to be careful, though, that doing this doesn't introduce unwanted ghost images into the optical system. If this is a problem, what can be done is a non-optical stress balancing back surface coating can be designed to achieve this. So this is a coating that's designed to index match either the substrate or the exit medium, which has minimal optical characteristics but provides the counterbalancing stress necessary. And this can be put on the back of an unused back surface on the optic, or it can be put underneath an anti-reflective coating, for example. And so these can provide a counterbalancing stress to maintain flatness. Again, what's necessary is very good characterization of your coating stress so you know exactly how to design this backside coating. And lastly, if no solution can be found to maintain the flatness, it may be necessary to prefigure the parts. That is, the flatness change due to the coating is characterized, and the inverse of that is polished into the substrate, such that after the coating is applied, the optic is bent into a flat nature. Now, this requires multiple test runs up front. It requires multiple back and forth iterations with fabrication and coating, and requires very good communication and coordination between fabrication and coating, and requires high process control. PFG finds this to be an advantage for us because we have both fabrication and coating under the same roof, and so we can expedite that coordination and make it as seamless as possible. So in conclusion, understanding the effects of coating processes on post-coat flatness for high aspect ratio parts is necessary to achieve these tight tolerances on these parts. Optical engineers can use this information to better understand what's required to produce the parts that they're designing. In addition, the proper optical design, for example, the lowest aspect ratio as possible, can lessen the impact of the stress-induced flatness changes in coating. So PFG has in-depth experience using these strategies, and we optimize our processes with the best strategies in order to produce these tight tolerance, high aspect ratio coated optics. So if you'd like to speak about this topic more, we invite you to join us in the chat room where we can talk about it. Again, my name is Kyle Fortenberry, and I thank you for listening today.